Section 11.5 of Chapter 11 discusses the self-ionization of water, sometimes referred to as the auto-ionization of water. We recall from the previous video that we looked at about acid-base theories that water is amphoteric, meaning it can act as either an acid or a base. In pure water, the following self-ionization occurs. One water molecule acts like an acid and donates its hydrogen ion to a second water molecule, which acts as a base, referring to Bronsted-Lowry acid-base theory. When one water molecule acts like an acid, donating its hydrogen ion, it converts into the hydroxide ion, its conjugate base. So we can identify a water hydroxide conjugate acid-base pair. When the second water molecule acts like a base and accepts the hydrogen ion, it converts into the hydronium ion, which is its conjugate acid. So we have identified a second conjugate acid-base pair, this time the water hydronium ion conjugate acid-base pair. As I stated here, this is a reversible process. And you see that I have highlighted the arrow to the left, meaning that the equilibrium lies to the left. When this process comes to equilibrium, you have mostly neutral water molecules present. You only have a very small amount of hydronium and hydroxide ion present at equilibrium. Therefore, you'll remember that water is a non-electrolyte. It is not a conductor of electricity, pure water, because the amount of hydronium ion and hydroxide ion present at equilibrium is very, very small and not sufficient to conduct an electric current. This overall self-ionization equilibrium can be simplified and written as a dissociation, where you just show one water molecule splitting apart and forming a hydrogen ion and a hydroxide ion. So you recall that we identified that a hydronium ion and a hydrogen ion are synonymous with each other. This hydronium ion notation is the full complete form, and the hydrogen ion, both aqueous, is a simplified form of the hydronium ion. All hydrogen ions in water are being carried by water and are actually in the form of the hydronium ion. Notice that pure water is neutral because we can see in this dissociation, in this ionization, that equal mole amounts of hydrogen ion and hydroxide ion are produced. Equal mole amounts of hydronium and hydroxide ion, if you please. So because of that, because you don't have an excess of either the acidic or the basic ion, an excess of either hydrogen ion or hydroxide, pure water is neutral. So in all neutral solutions, the hydrogen ion concentration equals the hydroxide ion concentration, or we could say the hydronium ion concentration equals the hydroxide ion concentration. This is true for all neutral solutions. In pure water at 25 degrees Celsius, we stated the hydrogen ion concentration is equal to the hydroxide ion concentration, and those concentrations are measured and found to be 1 times 10 to the minus 7 moles per liter, or 1 times 10 to the minus 7 molar, which is obviously a very small amount, as we stated previously. So hydrogen ion concentration equals hydroxide ion concentration, and both of those values are equal to 1 times 10 to the minus 7 molar. If you take a look at equilibrium chemistry and the mass action expression for this equilibrium, you write the hydrogen ion concentration times the hydroxide ion concentration equals a constant. So capital K is referred to as the water dissociation constant. That's what the little W subscript is referencing. Water, it is a constant. It is an equilibrium constant, but because it involves water, a very important molecule, it has its own special name. Water dissociation constant, or ion product constant for water. Because it is a constant, it is a fixed value that does not change. Well, we just discussed what the hydrogen ion and hydroxide ion concentration is at 25 degrees Celsius. We know that value, so we can plug in for the concentration of hydrogen and hydroxide 1 times 10 to the minus 7 molar, and that gives us this very important equation. Hydrogen ion concentration times the hydroxide ion concentration equals 1 times 10 to the minus 14 at 25 degrees Celsius. So the ion product constant, Kw for water, at 25 degrees Celsius is 1 times 10 to the minus 14. Now, what will this equation allow us to do? It will allow us to calculate the hydroxide ion concentration if we know the hydrogen ion concentration, or vice versa. If we know the hydroxide ion concentration, we can calculate the hydrogen ion concentration, or if we know the hydrogen ion concentration, we can calculate the hydroxide ion concentration using this equation. And we see right away that if the hydrogen ion concentration increases, the hydroxide ion concentration will have to decrease so that the product of their concentrations remains equal to the water dissociation constant for water, 1 times 10 to the minus 14. So if one of these concentrations increases, the other one has to decrease in order to maintain equality with the Kw for water.